So good afternoon and welcome to this last online technology meeting of the year 2025. My name is Antonio Castello. I'm technology manager at Epic, in charge of all the laser related topics, also the biomedical members. And today I'm very happy to be here to talk about what's new in terms of developments and components for ultrafast lasers. This is a topic that we already touched a little bit during the year, but more focusing what is new related with laser processing of materials. So I'm happy also to discuss with some of you what is interesting in terms of new components, not only for this application, but for other topics that concern also the use of ultrafast lasers. And for those of you who doesn't know about EPIC, so this is what it is. It's a consortium of more than 800 companies related with photonics technologies, European ones, and our goal is to support them and help them to have a business, sustainable business in the different markets that they are trying to reach. Short summary of all the benefits that we offer to our members. So we have with access to market report, we help with human resources activities, with connection with investors or with startups and spin-off that want to be acquired or want to be related with venture capital companies, networking activities, technological requests. So if any of these topics is interesting for you, please feel free to contact me to discuss more in detail. If you are a member and have a request, also feel free to send me an email with a specific request about what you need regarding these topics. And regarding networking, this is a list of the future activities, so I encourage you to go to our website to see what's happening in the next months. Of course, in January, we will be really focused on Photonics West. So regarding the physical meetings, we will have a lot of activities in San Francisco. So we invite to all of you to check what is happening. We will have lunches for the members, receptions. We will have the typical Epic run in the morning. So you are more than welcome to join us and enjoy all these activities and to find new opportunities of discussing with photonics companies in a nice environment as it is San Francisco. In particular, I want to highlight the breakfast that we have every year to talk about the EU projects, the pilot lines and innovation hubs. So we'll have a presentation initial by Michael Levy to give us some tips and advice about how to participate in EU projects. And then some of the projects that we were involved, will present also their activities, the results, the goals for the future. So you are interested in knowing more about this world, you can join us in the breakfast on January the 20th. And also I would like to highlight the networking reception we will have at the very same day in the evening in San Francisco, close to the Moscone Center. So as I mentioned, feel free to go to our website and check what's happening there. And I would like to see you there. Looking forward also to travel to United States to see what is new in photonics in this nice exhibition. And regarding other events, of course, defense is a very important topic. So we will be present at the Optro exhibition in France. So we will have a technology session in laser systems for defense applications, and another specific meeting for photonics for defense, where we will cover all the topics related with photonics technologies for this field, hosted by Exosense also in France. And the last one that I would like to mention is the integrated photonics and packaging typical technology meeting we have every year. And this time we visit the Netherlands, the fixed facilities in late February 26. And we continue also with the online meetings, not only technology that we will talk today, but also related with human resources, sustainability, also the new product releases of several of the members. And I want to highlight a few of them that they will be focused on lasers, and they are already planned for the next months. So we'll have a technology meeting on specialty optical fibers for lasers. It will be in February 26, 23rd February 26. We will talk about the different developments related with these optical fibers used for the manufacturing of different lasers. We will talk also new trends in laser welding, on the fly and handheld are going to be two of the topics we would like to discuss, but also other new developments in this field. We will have one focusing laser processes for the semiconductor industry, and another one in the specific manufacturing processes used for manufacturing semiconductor lasers. So not related with the use of laser for material processing, but what are the technologies used for the manufacturing BCL, BLC, different kind of lasers, diode lasers that can be interesting to talk about. And also, the main one that is going to be next year is the technology meeting on new developments for laser microprocessing. We will visit this time the Bordeaux area. We will be in Talents at Amplitude facilities on November 4th and 5th. So we will talk about cutting, drilling, dicing, micro welding, surface texturing as well. So the different processes that are interesting and involve the use of ultrafast lasers. So I'm sure some of you will be interested. So feel free also to come back to me if you want to discuss the details about these meetings. And coming back to the meeting today, we have a quite tough agenda, so we can already go there. We have quite a nice set of registrations covering the different parts of the supply chain. So we will use this slide to put it in the website. So feel free to check afterwards all the companies registered who are interested in this topic. And I would like to thank you, our sponsors for today, because it's important to have the support of our members in these meetings. So thank you to Optosigma, manufacturer of optical components, optomechanics as well, and different sub-assembly subsystems. And also thank you to Asfericon, that manufacturing freeform lenses and other optical components. So thank you for your support. And we can go already with the agenda. So we will start with a presentation by Lasea. So it's a pleasure to introduce you to Guillaume Simczak, Sales and Business Development Manager at this company, and he's going to present the Tool Touch Pro for laser micromachining. So Guillaume, I know that you are in a hurry today, so thank you for being here, and the floor is yours.
Okay, so thank you very much, Antonio, for this nice presentation. I will share my screen. Going for full screen. Okay, just let me know.
Everything good, Guillaume.
Okay. So thank you very much to having me today, and also thank you again, Epic, to organize such a nice event where we have definitely the opportunity to present our new development. And so today I will talk about a new module that we developed called LS Profile. That is a tool touch probe that is designed for laser micromachining. And so today, that's my agenda. I will first quickly introduce Lasea. Next, the state of the art for tool touch probe, and then finally our solution. So a few words about Lasea. So our vision is to drive innovation in photonics for a better world. So how we do it? In fact, we build a micromachining laser system. We mainly integrate femtosecond laser into this machine, but not only. And we build this machine over 3 facilities. One that is at the headquarters in Liège, represented by the picture on the right part of the screen. Another site in Mons, close to the French border with Optech. And finally, 2 sites in France. One is Laser Cheval that we acquired something like 2 years ago. And finally, Lasea France, where I am located, and where we developed also modules that we integrate in our machine, but we can sell also outside the group. And so the modules that we'll talk to today, it's developed by the French entity. Just in terms of market, 3 main markets: luxury, everything linked to watch and jewelry; medtech, mainly tubes like stents, catheter, and also intraocular implant; and finally electronics, where we do plenty of stuff like micro drilling, selective ablation, engraving, and so on. Of course, everything supported by the research and academic environment that is key for us to be in advance for our development. And here, so we have machines all over the world, and a picture of our office. Let's talk about Tool Touch Pro. So today, state of the art in CNC machine, the Tool Touch Pro is very well known. Everyone knows that the tool, in fact, it's something to change. It's a wear part, and this part has definitely an impact on the quality of the part that you produce. And so it's very common on this CNC machine to have daily routine to check if the tool is okay, have the right shape, right performances, and so on, and be sure that the machine is a good condition. But what about laser system? In fact, in the laser system, we have an issue because our tool, the real tool that we use, okay, it's light, but the light that we want to use, it's at the focal point, as you can see on the picture. And this is where you have interaction between the light and the material. So if you put any tool, you have a risk to damage it. So what is commonly do, in fact, we do a lot of assumption at the end of the day, because we can first of all make raw estimation about what the focal point can look like with some mathematical formula based on the optical path. And you can also look at different parameters over your beam path, or you can even monitoring over the lifetime of the machine or over the day. Or also you can attenuate the beam just to try to see what happened at the focal point. But at the end of the day, you never see your tool. You just estimate or try to expect what your tool looks like. And so most of the time, the result that you have and you expect, definitely, it's quite a round shape beam, well positioned. But in reality, you can see such a kind of things by having a non-homogeneous beam and with some drift if you change few parameters over your beam path. Also, I say that you can check the beam at lower power. So it's definitely something that you can look. So you can look at the focal point a bit upper, a bit lower. But for example, here your process is not working at 9 watts, but working at 50 watts. But as you don't want to damage your tool and camera, that's the picture that you have. And so for you, it looks good. So you say, okay, I can increase the power, start my process at full power, and everything should be okay. But if you start to measure it, you can see that more you increase the power, more you see things all over the process of increasing your power. And here at 33 watt, you can see that your beam and also in the power in between, your beam change, the beam size change, and so on. And you don't have the same thing that's at the beginning. And this is definitely an issue linked to the self-focusing at high intensity. And so as you measure your beam at very low power, you increase your process and you start to use your tool at the end with the wrong beam profile. And so the result is that you are not really satisfied with the result. And so you try to optimize parameters and try to work on your jobs to compensate, in fact, this deviation. But if you have a tool to measure it, you will definitely use less time to try to develop your process or try to compensate things that was working at low power. So that's why the probing process is key. And so our solution, what we bring today on the market, it's a module called LS Profile Spot. And it's a module, so you can see the cross. This is where you can place your focal point. You can use it at 100 watt, 1 millijoule using ultrafast laser. We even test it up to this value, but more short term. So it's still we are still improving such a kind of things, but it will be soon possible to use it at 300 watt, 500 watt, very high level of energy. You can measure spot size around 16 microns for very good quality. You can definitely go lower, but there is a norm to measure the spot size. And based on the camera that we have today, we recommend to measure a spot around 16 microns. And this tool can be used for any type of wavelengths. And so with this new tool right now, you can definitely probe your tool and see what's happened, thanks also to our software that we developed to help the use of this tool. One of the key elements is the automatic detection in the camera field, because as you are looking for quite small spots, it's not so easy to detect the point. And so the software automatically detect it. There is a lot of automatic stuff that happen that at the end, it's really a plug and play system that allow you to measure the spot size, not only in terms of size, but you can also track the position of your tool over different routine, and also to record data and to see if your beam is stable all over the time. And so here I will show you some integration that we did in our machine. So on the right part, you can see some processing area, and on the left, the LS profile spot. And from time to time, we move the stages just to check if the spot size is okay. And if it's okay, we can launch jobs and make the production. Another integration that we did in our new machine, the Neo machine, where we have two heads and two parts that are processed in parallel. And here it's definitely key to be sure that both heads have the same beam quality and the positioning is still at the same area. And so again, we have some routine going left or right before to launch jobs to check the beam and to monitor it over the production. And finally, a last, again, example where you have in the middle, again, the processing area, and on the left, the camera. So today, tool touch probe, it's possible. You can definitely find a tool available on the market, on the shelf, to check your tool using ultrafast laser, high power. It's also possible. Green UV wavelengths, it's accessible also with the same module. And this gives you the possibility to track the beam at the focal point. So this is it for me for today. Thanks a lot. And if you have any question, feel free.
Thank you very much, Guillaume. So now we have time for questions, so you can raise your hand. Also, if you are not available in the camera, use the webinar chat. Any question for Guillaume? I can perhaps start with a question about the frequency of the measurement. Perhaps you know more your case, the case of LSEA, right? How often do you need to check your spots?
So today we launch routines, like in fact CNC machine, just before to start a production. For example, that's definitely a key moment where we measure the spot at the focal point, just to be sure that the machine with all the different sensors is ready. And then if you have very, very long production, maybe in the middle or every X minutes, you can check it. And it's very easy and fast measurement. In fact, as we put it on very fast stages, it's a matter of, let's say, maybe 1 minute maximum. But yes, it's very fast.
And any idea in going in a kind of live measurement in the future? So having like kind of beam
Yeah,
splitter that sends some part of the
definitely,
beam?
it's something that we have in mind, to have a live measurement and live adjustment of the machine to avoid any drift. So today, already with this tool, we have some back calculation, especially if we see a small drift of the beam positioning. Right now, our machines are capable to take this drift and to compensate it. Okay, we put some limits to avoid any big drift that can be caused by, I don't know, external reasons, but all the minor drift are today compensate. And this is how today we reach machine with repeatability less than 2 microns.
Okay, very good. I don't know if there is any other question. Yeah, I have a question in the chat from Excel, Omar Sani.
Yeah.
The question is, what is the root cause for the beam instability observed at high power levels? You mentioned self-focusing, but it's happening in the optical fiber inside the laser system.
So yes, what we see today on with ultra-fast laser, and definitely with more with advanced component, where we definitely, for example, will precisely check the polarization. We have also some module that can compensate the taper. So you bring more and more, in fact, optics in your beam path. And so this can generate self-focusing. So it's the first reason with a high power laser to have self-focusing, because you don't have only reflective optics, you have also optics where you go through. And again, as you do some assumption with high power, you see, okay, at low power it's okay, but as soon as you increase the power, you start to reach some limits, and in fact, you can generate self-focusing. And this is one reason, but at the end, this is something that today we detect in our design. Things definitely that we can track. For example, it's the environment of our customer. We see that we ask them to have a very stable environment. We put a lot of compensation, but from time to time, there are external things that happen, and typically the drift of temperature, when you have a very precise process where we talk about microns of precision. All parameters have its own importance, and definitely a very small increase of temperature or something like that can impact the beam positioning and size. And so that's why it's definitely key to monitor it and to measure it.
Thank you, Guillaume.
You're welcome.
Good. So I don't see any other question. So thank you again, Guillaume,
Thank
for
you very
being
much.
today, for sharing all this information with us. And Guillaume probably needs to leave. So if anybody's interested in reaching him later, feel free to also send me an email and I can connect you with Guillaume.
Perfect. Thanks a lot.
Thank you. Thank you, Guillaume.
Yeah.
So we can move now to our next speaker. So we have a presentation by the company Holor, that is a company developing and manufacturing diffractive optical elements, micro-optical components. And we have today Nathan Kaplan, is the CTO and R&D manager at this company, and he's going to present the variable depth of focus bezel objective for laser glass cutting. So Nathan, thank you for being here today.
Thank you for the kind introduction, Antonio, and thank you, EPIC, for having me. And I will start our talk by sharing a presentation, otherwise it will be a bit boring. Okay, so before I start, I'll not make an outline since it's a short presentation. I'll just talk about who we are at Holor, what we offer generally for the ultra short pulse industrial laser applications, including processing, etc. And then I will go into our latest product for bulk transparent material modification, such as glass cutting and other applications through glass via, which is called the VB module, or variable bezel depth of focus objective. So a bit about us. One second. Since my presentation is not responding. Okay. Holor, as you see, we were founded 37 years ago. Yeah, soon 37 years ago. And we are quite experienced in the shaping of laser light through micro optics, especially diffractive optical elements. We originally started with CO2 lasers, and now we cover everything from the deep UV to CO through all the industrial laser wavelengths. We are located in Israel, in Nes Ziona, near the Weizmann Institute, and we have, of course, good connections with both the academy in Israel, in Europe, and of course in the industry. And we're also now a sister company of within the Tech Invest holding group of ScanLab and Blackbird and other companies in the group. So we have good feedback from the laser integrators regarding the requirements of ultra short laser applications. hopefully a good feedback. You will tell me. We were the first company to deliver diffractive optical elements for commercial use. I mean, they were done in MIT before that, but no one sold them. And we are based on good connection between the ability to design the optical function and our ability to simulate them, ability to produce them and give the customer a good estimate of their performance in their system. And we have a very diverse portfolio of diffractive optical elements and other types of micro optics, as well as modular solutions for some cases, as I will present here today. So, as I said, HoloOr develops DOEs. For those of us less aware of what are DOEs, these are thin purely phase windows. We mostly do transmissive. We can also do reflective for customers that want to. Typically, they are done on fused silica for the wavelengths discussed for ultra-short laser pulses. These windows are very thin. They have almost no temporal aberration, no chromatic dispersion. Therefore, they don't ruin the ultra-short pulses and are very useful for applications shaping them. Instead of having 20 millimeters of glass, you can often have 1 or 2 millimeters of DOE thickness. The magic they do is by having a phase profile that's etched on their faces. Here, we do it in-house using lithographic methods with very good accuracy. And therefore, the elements themselves have absolute angular precision, or nothing is absolute, but 10 to the -5 or -6, which is practically absolute angular precision due to the fact that it's lithographic tolerances. They have high laser damage thresholds, similar to a fused silica window coated with good coating, and they are very thin and compact. Of course, one of the main advantages is you can combine multiple optical functions. You can combine, for example, a diffractive lens with a diffractive prism with a beam shaper or a multispot or whatever in a single surface. Mostly HoloOr has three main product families, which are the beam splitters that split a beam into an array of sub-beams or spots at the focus plane of the f-theta. Beam shapers, which shape a beam either analytically, if it's a single mode beam, or statistically through controlled flat top diffusion. And beam foci elements that manipulate the beam along the depth of focus, which is what I will discuss today. For example, the simplest one are diffractive axicons, which generate a bezel beam that has a depth of focus that is much larger than a standard Gaussian beam. We also have multifocal, tilted beams, airy beams, whatever the customers need. So before I delve into the specifics of the VB module objective, I was asked to say what HoloOr can do for you, the classic EPIC question, and what we can do for you in EPIC. So what can HoloOr do for what you can do for us, of course. What can HoloOr do for you? We can provide high laser damage threshold DOEs and micro optics per requirement. Also, we have a huge catalog. You're welcome to enter our website. We can simulate our optics in your system, including ZMAX integration for many of the optics. And we like solving complicated beam shaping challenges, illumination on inclined planes, and various other exotic cases. And what you can do for HoloOr, of course, you can give us beam shaping challenges that are interesting and useful to solve. You can do application tests with our DOEs. We are often open to the idea that you receive the DOEs at a significant discount or basically at cost if you're willing to let us use the results for marketing cases. And we're always looking for partners that cooperate in European projects within the Horizon Europe framework. Yes, especially if the project has a laser task that requires some sort of beam shaping or other type of phase manipulation, such as Schack-Hartmann, etc. Could be everything. Okay, so let's go into the depth of our talk. I want to talk about optics for laser glass cutting and generally laser bulk modification using ultra-short pulses. As most of you know, to achieve the energy densities needed to cut glass with good efficiency and speed, typically IR laser needs to be focused down to 1 to 5 micron spot, not much more than that, with industrially available ultra-short lasers, which is typically 20 to 40 watts, not more than that. Now, when you focus the laser down to such a spot, first of all, it rules out most of theta. You have to work with an objective. You cannot work with a scanning regime because this is a high NA system by definition. You can calculate the NAs needed to get a 2 micron spot with the 1064 nanometers wavelength. And when you focus it down with a Gaussian beam, you don't have the depth of focus to cut any sort of reasonable glass or to process a true glass via in any sort of thickness above a few tens of microns. So even if you want 80 microns, it's not feasible with such spots. So the way that this process is usually done is through some sort of focal manipulation. For example, turning the beam into a Bessel beam, which has the energy focused in the central lobe and most of the energy in external rings. And then at each focal plane along the focal direction, you have a new focus. One of the ring becomes the focus. So this is nice and fine, and we can make such optics. These are called diffractive hexagon or elongated focus elements, but they are static. You just get a certain depth of focus with a certain focusing optic outside. Now, many of our customers, first of all, they want a full solution. They don't want to add their own external objective. And second, they are not sure what process parameters they need to get the glass cutting or glass processing, etc. Or sometimes it's just modification, right? Because you sometimes have different materials, different thicknesses, and as all of you have tried to develop a laser process, know it's complicated. Yeah, so any degree of freedom helps a lot. We heard this requirement, and we have developed the VB glass cutting module or VB variable Bessel objective. And the idea is that you have an optic, which is a module, that does everything. You just need to come into it with any beam size from 3 to 8 millimeters. And at the work distance, which is 7 millimeters after the edge of the module, typical for such a high magnification objectives, you will get a Bessel depth of focus region, as you see here down below the graph. And by rotating this ring, you get a variable depth of focus around the same work distance. There is a slight work distance shift of 0.1 millimeter from one edge to another, but generally you just get the same lobe. The Bessel lobe is not imaged, so it always stays the same 2 microns along all the variable depths of foci. Even if you are working with 80 micron depth of focus or 1.5 millimeters in air, everywhere you get the same Bessel objective. So this is not an imaging Bessel objective. It works in a different principle. It uses our diffractive optics. It has very little glass. The total glass path inside this optic is less than 10 millimeters of fused silica. So it doesn't have a lot of temporal dispersion. And because it only changes the depth of focus, it is easier to develop a process to fit your glass because you're not changing also the size of the Bessel spot when you're imaging it at a different ratio. So this is a complete optical solution for the development of processes for the modification of transparent materials using ultra-short lasers. And it can be, of course, adjusted for all the range inside that, and similar to an NA 0.34 objective, which is typically used for such applications. We offer this at both IR wavelengths and at UV wavelengths currently. Green wavelengths currently. UV is maybe possible in the future if needed, but right now we're offering it at IR, one module for 1030 to 1080 nanometers and one for 515 to 532 nanometers. And it can be very useful to develop the process parameters, or if you have a machine in your shop that needs to be versatile, that sometimes cuts a certain thickness of glass, at some other times it works on a different thickness of glass or a different index material. And each of these objectives is individually tested for performance in our custom built setup at Holor. We provide the report with the module itself, so you can be sure that it has the performance. It's tested at both edges of the range and in the middle. And the installation is quite straightforward. It comes with its own manual. If you're interested, you're welcome to scan the QR code in this page and get a link to this module. So that's it. Thank you for allowing me to present, and feel free to ask questions.
Thank you very much, Nathan. So we have again time for questions. Yeah, there is a question from Celia from Riven. Can you do it live, Celia?
Yeah, sure. Hi, everyone. Short question. So you mentioned that your module works in IR and green. Do you also have the capacity to develop system around 2 micron?
Yeah, no problem. Where fused silica is transparent. We currently do not offer it, yes, but it is a matter of a few weeks to develop based on the shape.
Okay.
chassis, let's say. Yeah, the same body.
Okay, thank you.
Any other question? I have a question. Oh, well, we have Optoprim. Dimitri?
Hi, Dmitry here from Autoprim. Maybe a silly question, but could you please explain why you would want to change the depth of focus without changing the spot size?
Okay, so generally when you are working with developing the process for laser glass cutting or other processes, because we're not saying what you are doing with this module. If you are using some imaging method, then if I'm increasing the depth of focus by 2, I'm increasing the central lobe from 2 to 4 microns. Now my power density is dropping by a factor of 8. Yeah. However, if I'm using this module, I'm increasing depth of focus by a factor of 2. Yeah, I'm still just losing energy density a factor of 2. So it is much easier for me to hit on the right energy density to cut the glass, yeah, because I'm only changing one parameter. I'm reducing it linearly to the change in depth of focus instead of simultaneously changing it like to the third, yeah.
Okay, thank you. I was just wondering why not to take the longest one and work with it, but you're right. You of course need more energy to.
Yeah, you're spreading the energy in Z.
Yes, thank you.
Oh,
Any other question? I had a question regarding the combination of this solution with the beam shaping that nowadays is quite hot topic. How do you see combining this variable focus with kind of beam shaping that you apply to the beam?
So generally, it's not so possible to shape both in Z and in XY. Also, typically not beneficial because they are trying to reach the highest energy density. If I have a Bessel beam, I'm already doing beam shaping in XY. If I'm interfering with that, with doing something in XY, then typically it will ruin the Z propagation. The only type of beam shaping that I could think this would be combined with would be a multispot, which will generate, let's say, 3 foci, one, and there it's possible to develop such a model. It's not trivial. We need to, but if there is some demand, we could, in theory, develop such a module that in parallel will do several channels if someone needs that.
Yeah, very good.
That is possible.
Yeah.
Thank you. Interesting question.
Yeah, because it's something that we discuss a lot nowadays, and it's true that there are different kind of possibilities, so it's good to know how to interact with all of them. So I don't see any other question. So Nathan, thank you very much for being here today, and I recommend you also to reach them if you are interested in discussing more in detail your needs. Thank you, Nathan.
Thank you, Antonio.
And we can move now to our next speaker. So we have Valentina Shumakova, product manager at the company Ultrafast Innovations. Ultrafast UFI is a manufacturer of different optical components, also diagnostic devices, and she's going to present today the nonlinear pulse compression system. So Valentina, the floor is yours.
Thank you, Antonio. Thank you for the invitation and kind introduction. I know that the topic which we originally suggested here, it was related only to the post-compression system, but my presentation today is going to be a bit broader because Ultrafast Innovation, you can see my screen, right? Yes, Ultrafast Innovation is a company which provides multiple product lines. And most of the people know us as a company which provide high dispersive mirrors or chirped mirrors, as most of the people call them, which are very relevant for the pulse compression. However, it's only a small fraction of the products which we are actually producing. We also supply high laser damage threshold mirrors, dichroic mirrors, and customized optics spreading from mid-infrared to the XUV spectral range. We not only sell these optical components, but we also use and test them ourselves. We assemble them into the devices for pulse characterization and manipulation with the spectrum of the pulse or with the pulse polarization. And these devices we can even assemble into the entire beam lines, which covers everything from post-compression of the laser to the generation of coherent XUV light at the customer wavelengths. It can be visible ultraviolet, it can be soft X-ray, water window harmonics. And before we are going to the new developments, I want again to go through our device product line. which covers the broad range of parameters. So basically, we can start from the laser cavity and characterize the contrast of the laser pulses up to the 14 orders of magnitude. And then we can take these picosecond, sub-picosecond pulses, broaden them in multiple stages, and generate few femtosecond pulses, just one cycle of the optical field, focus them down in our XUV beam lines, either in the enhancement cavity, if we talk about megahertz repetition rate and small energies, or single pass through the gas jet, if we talk about millijoule level of energies, and reach up to the kiloelectron volt, with which also can be measured with in-house built spectrometer, which we called Everest. And on top of it, we can provide extra meanings of characterization and manipulation with XUV pulses or infrared pulses. And we also produce the devices which allow us to have a feedback on the optical components which we produce. It's Glacier and Gobi, it's white light interferometer and cavity ring down reflectometer. So to all this already very diverse range of products, this year we added 5 new, and I'm going to briefly introduce them today. Feel free to reach me after this meeting if you're interested in any of them. I will start with Savannah Squared. It's our cascaded system for spectral broadening and large post-compression factors. Then I will quickly introduce you to Kauai. It's ultra broadband quarter wave plate, which is introducing almost no dispersion. Then I will briefly show you the new generation of UV coatings, which is suitable for the post-compression of UV pulses or harmonics from 1 micron laser. And then I will discuss spectral shift and contrast cleaning and the compact post-compression systems. And finally, show you a teaser of a new beam line coming, which is working up to the 600 electron volts. So why do we build cascaded post-compression systems? For a very simple reason. Most of the labs don't have enough of space to broaden the spectrum enough to cover the range from picosecond to the few cycle in the single fiber. Typically, it will take 7 to 10 meters of propagation, and not every lab has it. Beside it, it gives us other advantages such as the increased transmission or higher contrast between the pedestal and the peak. On top of it, we can fold this system into quite compact arrangement, 3 by half meters. And in this arrangement, we can enter with industrial sub-picosecond 1 micron laser, post-compress it first to 30-40 femtoseconds, and then couple this 30-40 femtoseconds pulses into the second post-compression stage and reach few cycle regime. Here, I want to point out that we are working with the different technological solutions. It's not necessary to be fibers. We're also working with multipass cells. Just in this particular case, to demonstrate the capabilities of the systems, we went to the 2-fiber solution. At the end, we reached post-compression factors of 30 to 35. Our initial pulses were slightly longer than 170 femtoseconds, and the pulses at the output of the systems were as short as 5.7 femtoseconds. Here you can see the full spectrum of the system. And unfortunately, at the moment, we do not have the right mirrors to compress the full spectrum. Our mirrors are covering only 700 to 1300 nanometers, but we are working on the new generation of the chirped mirror to cover the full spectrum range and demonstrate even shorter pulses from the same system, hopefully. Another limitation here is the measurements techniques available now at the market, because we want to be oriented towards the commercial products, not to the customized built systems for pulse characterization. The overall transmission of such cascaded system is above 60%, which is quite good for the optical fibers, and the footprint is only 50 by 300 centimeters. This system, of course, works at the linear polarization, but if one wants to work with a circular polarization or elliptical one, or want to switch between them easily within the experiment, we can provide a solution for this too. Here is Kawaii. It's a reflective base quarter wave plate, which consists of several mirrors arranged in the way they introduce retardation of quarter of the wavelength when the device is rotated to the 45 degrees. There is internal rotational stage inside, motorized. It's controlled by the software. And the beauty of this device is that it works in the spectral range over the octave, and it doesn't introduce extra dispersion into the pulse. So the GDD value is limited by 3 square femtoseconds. That means that it's suitable for the few cycle pulses or broadband OPAs and OPCPAs. So a lot of people here were talking already about micromachining, and when people work with micromachining, it's not only ytterbium lasers themselves, but also optical harmonics from these lasers. And nowadays, people are exploring which pulse duration would be more beneficial for the micromachining, which one would give the cleaner cut and smaller features, which would reduce the thermal ablation effects. And of course, there are big achievements already in this field when we talk about 1 micron. When we talk about harmonics, especially third and fourth optical harmonics, the limitations here are optical coatings for the post-compression of these pulses. Even though these pulses can be efficiently broadened, the quality of the chirped mirrors was not sufficient enough to efficiently compress the pulses after the nonlinear spectral broadening. So here you can see the reflectivity curve of the new chirped mirrors for 250 nanometers, and it's above 98% in the whole spectrum range, which is necessary to cover to post-compress UV pulses. And here you can see this almost vanishing line. It's the old reflectivity of the mirrors, which is 80%. So we increased it significantly, and now we can provide very efficient solutions for the post-compression of UV pulses. Beside it, as I mentioned, we are working on the cleaning of the contrast of the pulses, which is also potentially a big problem for the micromachining, because even though this contrast is orders of magnitude lower in the intensity than the main peak, it still might contain significant fraction of energy from few up to the 20%, depending on the laser system. So our solution here is to shift the central laser wavelengths from the spectral region where there is amplified spontaneous emission, where there is a coherent background from the stretcher and compressor towards the red side. And this can be done very efficiently with efficiency of 70% sitting in this peak. This peak can be further isolated with a dichroic mirror. And then we can measure the contrast before and after this process. And you can see that we can significantly, by 3 orders of magnitude, decrease the pedestal of the pulse. Therefore, we can achieve cleaner cuts, for example, if we talk about micromachining. And as I promised, our latest achievement is reaching soft X-ray, coherent soft X-ray driven by 50 kilohertz laser. So it's a commercially available 2 micron OPCPA system built by Fastlight and Amplitude in collaboration within a big research project. And with this OPCPA, we used our in-house built beamline. So it was everything from the generation chamber up to the spectrometer coming from Ultrafast Innovations. And our latest achievement is covering the spectral range from 300 to 650 electron volts with photon flux 5 multiplied by 10 in power of 5 photons per second per electron volt. And as many of you probably already heard, we also recently announced a strategical partnership with Alio Labs, and we're very excited about it. We're looking forward towards our new achievement in 2026. And with this, I would like to thank you for your attention.
Thank you very much, Valentina. So we have, again, time for questions and comments. Any question for Valentina? I will perhaps have a more general question for the future because you are also involved in this compression task. So how do you see the requirements for future interesting sources, attosecond sources that are happening nowadays, but perhaps will be also prevalent in the future? The requirements are different from the sources nowadays. Do you see an evolution in the requirements that needs to report in terms of development? How do you see this market?
Oh, it's a very interesting question and very broad one, to be honest.
Yeah.
What I see is that there is a shift in the interest in the researchers' minds, because we mainly work with research customers.
Yep.
That if before they wanted to buy separate elements and build their own beam lines, nowadays they come to us with the idea of the experiment and they just describe what they want to do. And we need to be the one who suggests to them a laser system, which is very unusual. Like a few years ago, it wasn't like this. People were way more involved into the laser specifications. They wanted to control it. They wanted to be able to tune it. While nowadays, they want to concentrate more on the experiment.
Okay, very good. Good to hear. Any other question for Wi-Fi? Well, if not, if there is any other question in the future, please reach Valentina for this discussion. So thank you for being here today, this afternoon. And we can move now to our next speaker. So we have a presentation by Sabina Kuprenaite. She's the head of R&D at the company Optoman, that is quite well known for their film coatings. So she's going to present today lifetime engineering non-degrading optical coatings for ultrafast laser operation. So Sabina, thank you for being here. The floor is yours.
Hi, thank you for the presentation. Do you see it, the first question?
Yeah, everything good.
Okay, perfect. Okay, Okay, so thank you for the nice presentation. And today I would like to talk about lifetime engineering, actually. And I would like to present the non-degrading optical coatings that were developed for reliable ultrafast laser operation. But first things first, actually. So I would like you to meet Optoman. Optoman is a super optics hero. So today we have 56 professionals that design and manufacture high power laser components for various applications. So spanning from industrial laser processing, medical systems, to defense and fundamental research. Here at Optoman, we focus basically on ion beam sputtering technology, exclusively on that technology, because actually delivers exceptional process stability and reliability, combined with ultra-low scattering and finally dense impurity-free coatings that actually enhances the performance and durability under intense laser conditions. So all that said, we also understand here that high performance optics are only as good as their lifetime, especially in the ultra-fast laser systems. So when talking about lifetime, we should clearly understand what degradation is, the so-called fatigue effect is. So in the ultra-short pulse regime, optical coatings typically fail in two different ways. So one of them is the catastrophic damage, and that is a sudden and visible failure where intense laser radiation creates a crater on the surface. So basically light scattering increases immediately and basically the system stops functioning. And the second one is the color change, and that is kind of a more subtle, but it is an equally critical mode. So usually the color mode is usually observed.
Sabina, just a moment. Are you changing the slides? Because we only see the initial slide.
Oh, sorry. Yeah, I was actually, but okay, sorry. So yeah, so this is the slide about Optoman.
Yeah.
And yeah, here. So here is the slide. Okay, I am sorry. I thought I was. So yeah, so here you can see the two distinct damage modes. So as I was talking, the catastrophic one and the color change one. So yeah, so the color change one is usually observed at lower fluence levels and at an earlier stage, and it eventually leads to catastrophic damage. So unlike the catastrophic damage, the general nature of the color mode is still quite unclear. But what is important is actually to separate those damage modes and to evaluate the lifetime for each of those modes separately. As you can see in this measurement, because the catastrophic mode seems quite okay. And then we notice the color mode, you know, that after some time it starts degrading quite fast. So let me just, okay. So, I'm sorry. So what is the degradation effect on the ultrafast laser operation? So basically it limits the lifetime, it causes unexpected downtime and maintenance, it increases the total cost of ownership, and actually it is a major bottleneck for the UV laser systems. So like any high performance system, optical coatings must be trained for endurance. And how can we actually build this strength into the coating? So can the exercising help, or it can be a meditation, you know, or can the psychotherapy sessions help? Actually, we don't know, but we think that the answer starts with actually firstly understanding the failure itself. So yeah, so we performed actually a detailed analysis of the color damage site. So here you can see a high contrast images showing typical morphology before and after exposure. What we did actually, we performed the XPS analysis to estimate the stoichiometry of the color change free area and the color change area. And actually what we noticed is that the color change free area had a stoichiometric silicon dioxide, while the color change area had like a 20% of silicon oxide with oxygen deficiency. So this deficiency can cause a localized absorption and finally the degradation and the damage. One of the other tests that we did was a FIB cross-section and the elemental analysis of the damaged sites. And even though the elemental analysis is qualitative, not quantitative, but it confirmed actually the oxygen deficiency. And what we saw that there is an oxygen deficiency, especially at the first layers of the coating, top layers of the coating. So actually we performed many more analyses than I presented here today. And we understood actually the origin of the degradation. So we decided, you know, that the next step should be an action. So yeah, so here is the standard design and the materials that we were using. So the LIDT measurements of our basically standard component. So we thought, okay, we would move to coating design modifications at first. So what we managed to do to increase the catastrophic damage threshold, but you can see that the color mode is still there and it's quite harsh. We managed to delay a bit the color change, but still it was not enough. We decided to move to material modification. So after several iterations, we managed to delay quite a lot the color change and to reduce it, but still it was not sufficient. So basically building on all the findings and all the information that we gathered from the experiments, we combined the most effective solutions from coating designs and from materials. And actually here how the best of both worlds look like. So we performed coating design and material modifications, and we managed actually to obtain coatings without color change. So basically today, LIDT measurement service providers such as Lidaris can use their measurement characteristics to extrapolate the lifetime. And here is the extrapolation of the lifetime. And this enables actually the reliable lifetime prediction. Another nice effect of this technology, the unexpected effect, was the increase in thermal conductivity. So basically, the samples were tested in a femtosecond laser system, and the client tested 2 mirrors from competitors. So here is the mirror 1 with a notable increase of temperature. The competitor number 2 mirror had a slight increase of temperature, and the Optoman's non-degrading mirror actually had no increase of temperature. What is interesting that the absorption of Optoman's mirror was higher than that of the competitor's mirror, 82 ppm compared to 57 almost ppm. But still, thermovisual measurements showed that this non-degrading technology might result in a better thermal conductivity. So I would like to complete with a nice note, with a proud note, that our non-degrading technology actually won the Innovation Award at the Laser Workshop of Photonics in Munich in 2025. So we are super happy about that. So yeah, if you do have some questions, they're welcome, and thank you for your attention.
Thank you very much, Sabina. So again, we can go with questions. I have perhaps a question regarding the use below the 300 nanometers. Do you expect to have the same results, or will you need to investigate a little bit in the use of your coatings below 300 nanometers?
Actually, we applied the same technology for the 4th harmonic, so we do have the technology applied for 257 nanometer mirrors. So yeah, that works.
Very good.
And the lower is a bit limited, kind of, to the technology and dielectric materials, but still, you know.
And regarding the damage measurements, is something that you do at Optoman on your facilities? Do you collaborate also with other parties?
No, we collaborate. We outsource the measurements at Lidaris. They perform the lifetime measurements, so they are certificated. Yeah.
Very good.
Sabina, can you show me again the absorption of the coating? Sorry, I missed it somehow. Was this 2 ppm? Was it correct?
No, it was not 2. It was 82.
822.
82.
82. Okay.
82. Yeah, here. If you can see, it's 82.
What metrology did you take for that? So how did you measure it?
It's PCI. We measured it also in Lidaris, so we outsourced also. So they used photothermal common path interferometry to measure absorption.
Okay. Thank you.
Thank you, Guido. Any other question for Sabina? If not, thank you very much again for being here and for showing all this very nice work. Thank you and congratulations. And now, before moving to our next speaker, I would like to give some time to our member Aerodiode. So we have Adele Morissette, the CTO of the company, that she wants to share some of the solutions that they have for ultrafast lasers. So Adele, if you want to share your screen.
Yes, hello everyone. Thank you, Antonio and Epic, to give us the opportunity to give you a quick presentation. Okay, are you able to see my screen?
Yep.
Yes, so I'm Adele Morissette, the co-founder and CTO of Aerodiode. We are based in France, near Bordeaux. So I will have one slide presentation to give you a quick overview of products and focus on our solution for femtosecond laser makers and research teams. So we sell components for example, cedar, pump laser, but also acoustic modulator, free space, and also fiber coupled, and photodiode and semiconductor optical amplifier. We are able to provide solution, so to integrate this component into more complex electronic solution. We have also very good Swiss knife electronics, which is a pulse speaker electronic to be able to, for example, make frequency division in your femtosecond oscillator before amplification. But also we have a continuous and pulse laser diode drivers for single mode and multi-mode diodes. And we also have more complex subsystems like turnkey pulse speaker, integrated all-in-one AOM, RF driver, and our pulse speaker electronic together inside the box to have a turnkey solution. And our last product is very universal photodiode electronic to be able to measure your gigahertz, picosecond optical pulses, but we've also the ability to use low noise gain and switchable gain, which is also a Swiss knife in your lab to make your measurement of your laser pulses. That's all. Thank you, Antonio.
Thank you very much. Thank you very much, Adele. So I encourage all of you to go to the Aerodio website and also discuss with Adele your potential needs for the future. So thank you.
Thank you.
Thank you, Adele. So we can move now to our next speaker. So we have Mike Frede, CEO of the company Neolassi. Neolassi is a co-manufacturer of solid-state lasers, also amplifiers, now part of the AMS group. So Mike, the floor is yours. You are going to present the modular building blocks for ultrafast lasers.
Yeah, thank you, Antonio. Thank you for the kind introduction and for the possibility to give the presentation here today. So I want to talk a little bit about building blocks for ultrafast lasers, especially focused on the laser systems and laser amplifiers. So before I start, a few words. Neolase is part of AMS Technology since the acquisition of Neolase in 2024. And since that, I'm also responsible for the engineering at AMS Technology. So there are 3 engineering facilities all over Europe, which are focused on optics, thermal, as well as electronic solutions. So the AMS annual revenue is about 35 million euro with about 100 people. And we have different sales offices all over Europe. So in general, the idea is that we are trying to support the photonics, electronics and thermal industry within Europe. So give you a quick overview of what we're doing in the different fields. So from a little bit the Hanover as well as the UK portfolio, we have mobile lasers, Q-switch lasers, talking about optical amplifiers. That is a topic I would focus on later today. So we will cover the optics and laser side. So then there is a facility near Krakow where we do all kind of cooling loops, chillers, TEC controllers, heat exchangers. We all know that lasers produce heat, and we need to get rid of the heat by proper cooling solutions. And last but not least, we need to drive all the laser photons with some electrons. So we are also having a facility in Poland where we do our own laser drive, laser electronics, and also the TEC drivers. And if we combine that all together, we are doing assemblies which combines all optical, mechanical, and thermal solutions. So today I want to focus on the laser solution side. So as I said, so the Daventry side, the so-called company Alpha Light is focusing on nanosecond oscillators. So that's more like the long pulse story. We don't want to touch that today. I want to focus on the laser amplifiers and the combination of the laser amplifiers with different oscillators, so that we can cover a variety of different solutions for ultra short pulse lasers and ultra short pulse applications. So if we look into the amplifier technology in general, there are two different kinds of amplifiers which supports the amplification of short pulses. So the general architecture always looks quite similar. So we have an oscillator, typically it's a mode-locked oscillator with a few tens of megahertz in repetition rate that typically needs some pulse picking to reduce the frequency to the range of less than a megahertz down to 100 kilohertz. And then we can use the linear amplifier stages that are cascaded amplifiers, which increases the average power or the pulse energy of the mode-locked fiber oscillator, or we can use regenerative amplifier schemes where you have a resonator and an optical switch to couple the pulses into a resonator and then do the amplification into the resonator. So depending on the speed of the switch, so the regenerative amplifier is somehow limited in the maximum frequency, where the linear amplifier schemes has higher flexibility in terms of the amplified repetition rates. So if we go further into what kind of amplifier solutions we have, and if we look on the market, then the classical amplifiers are based on disc rod slabs, like the classical DPSS lasers, or we also have fiber lasers. So, and I want to quickly go into that to discuss a little bit the optimal pulse, the optimal amplifier concept, which we think for short pulse laser amplifications. So, and if we look into the gain for an amplifier system, so the gain is depending on the emission cross-section of the material, so the inversion as well as the length of the material. So, and if we go into that, then we can directly see the disc laser, which has a 200 micron of length. So it's a very, very thin laser crystal design. So it has a very short length. So we need to have quite some high gain or high pump power to increase the gain here. And that's the reason why the gain in a disc laser is typically in the range of less than 10 dB. So if we are looking into a slab laser is a little bit bigger and has, due to the fact that it's going by a zigzag, a much higher interaction length of the laser beam and the gain material. So that increases the gain to the range of 10 to 20 dBs. If we go farther up, so then we do the end-pumped rod solutions, which has the advantage that you can overlap the pump and the laser mode pretty much, and that increases the efficiency, which gives us something like 20 to 30 dB. And finally, the best gain in terms of what you can get out of the different amplifier concept is the fiber, because it has the longest length and it has a very, very short, very small emission cross-section, so a perfect overlap, which gives you the highest gain. But that does not mean directly that this is also the best solution for short pulse laser amplification, because we need to take into account nonlinear effects, which are typically driven by the intensity and the material interaction lengths. And I think you all know the intensity is driven by the pulse energy over the pulse duration. And as we are talking about short pulses, as shorter the pulse gets, as earlier nonlinear effects needs to take into account. So, and we have different effects here. I do not want to go through all the different ones, but in general, the topic is that we already heard about self-focusing, for example, in the first talk from the laser, which can limit the beam quality and can limit the amplification in general. We have optical damage, which will finally damage the material, and therefore no further energy or power scaling is possible. And then for sure other limiting effects, especially for fiber lasers. We have self-phase modulation, for example, and other effects like Raman-Briand scattering and so on. So if we take this into account again and compare that with our different amplifier concept, we can distinguish a little bit between which kind of amplifiers can be used for, let's say, medium average power scaling, where we have still a high gain, but reduced nonlinearities and reduced nonlinear effects. We went with the end-pump rod solution, which allows us to amplify milliwatt input ranges up to a few 100-watt power levels and up to millijoule pulse energies, which cannot be covered by the fiber, and which is still quite an efficient concept. And if you want to go to higher power levels, then you would go for disc lasers or slab lasers, for example, which then brings you into the power levels of 500 watt and above, and even much, much higher pulse energy levels. So over the past, we developed quite a lot of different amplifier units. So the typical start was neodymium vanadate, which is a 1064 nanometer based amplifier system, neodymium vanadate or neodymium YAG, which has some very high gain. We do more than 40 dBs out of a pre-amplifier unit, but it's limited in pulse duration at some point due to the spectral bandwidth of the gain material. So we went for ytterbium YAG, which gives us a much broader spectrum and therefore also supports femtosecond laser pulses. And we did a little bit of work in the range of 2 micron, 1940 by thulium, as well as 2050 by holmium. You see that there are quite a little family of different amplifier systems, which you can see below, which starts from low power milliwatt input power levels, where we can directly couple fiber-coupled mood-locked fiber oscillator, for example, and amplify that. And then there are free space optics, which then, or free space units, which then can be cascaded to scale the power into higher power levels. And I brought some examples here. So all is based on this very modular approach that you can cascade the different amplifier units to address different pulse energy or average power levels. So we typically start with a femtosecond mode-locked fiber oscillator, which covers pulse duration ranges, I think in the range of 500 femtoseconds, which are typically then chirped to something about 50 picoseconds. Average power levels are 5 to 50 milliwatt, depending on the rep rate. We're typically talking about 30, 40, or 50 megahertz repetition rate, which is then pulse picked and amplified. So when we cascade our ytterbium amplifier systems, you see that here we can cover different average power ranges from 10 to 200 watts, depending on the number of stages. Pulse energies goes to more than 1 millijoule of pulse energy. One interesting point here is also for amplification of high rep rate systems. So we do quite a lot of gigahertz system amplification, where we can do CPA-free amplification. So the system, due to the low interaction lengths and no low nonlinearities, so the laser crystals can support, or the laser modules can support up to 50 microjoule in a CPA-free regime. So that means we can directly amplify Fourier limited pulses up to 50 microjoule of pulse energy. So if we want to go beyond, and I think we also already heard an example of that here. So the ytterbium, depending on the gain narrowing effect, supports something like 600 to 900 femtosecond of pulse lengths, which comes out of this MOPA laser scheme. And if we want to go farther down in pulse durations, we did a combination with a nonlinear pulse compression cell. These experiments or these units were built up with N2 Photonics, for example. They have a multipass cell, and we could go down to 100 or even down to 50 femtoseconds by a cascading two compression cells. The advantage here is that we can do quite some high energy and average power levels with this technology and can cover the very good beam quality. And I think we saw that also in the previous talk. So the efficiency of these compression cells and the optics are quite nice these days. So that's a very nice tool from our point of view to scale the pulse energies even to lower pulse duration ranges. So give you one more example on the 2-micron. So here we took a laser from Inolas, which is a fiber laser, 1940 nanometer, and we amplified that with our NeoTap, with the thulium YAP-based amplifier system. The advantage here is that thulium is, as well as the neodymium and ytterbium crystals, are directly diode pumpable. So it's more or less the same concept as what we use for ytterbium and our neodymium systems. So the gain is much lower. So achieved an overall gain of a little bit more than 10 in this configuration here, but this allows us to scale from a few microjoule of pulse energy from that mode-locked fiber oscillator up to 20 microjoule of pulse energy and more than 10 watts of average power levels. So giving you an overview or summary with an overview of systems, what we have done in the past and which are all supported by this unique combination, I think, from taking different oscillators, which we take from the market, which allows us to address quite a few different pulse duration ranges and combine that with our amplifier systems or even nonlinear compression cells. So we can cover the range from a few tens or hundreds of picoseconds. So we're going down here. 50 picoseconds is a gain switched laser diode, which supports this pulse duration ranges. And then we are going further down, 10 picoseconds and below is a domain for mode-locked fiber oscillators typically. So with the neodymium platform, we are limited in the pulse duration of about few picoseconds. And then with the ytterbium platform, you can go down to 900s or below, depending on the gain narrowing in the laser material. And with the compression cells, as mentioned, so we can go down to 100 or even 50 femtoseconds. Everything based on a modular approach of these different systems. And with that, I want to finish my talk, and thanks for your attention. And I'm open for questions.
Thank you very much, Mike. Any question for Mike? I will perhaps start with a question about you show one example with Inolas, for example. What are your requirements when using your amplifiers with a laser from another manufacturer? Do you require certain time of connectivity in quality before the interaction with your amplifier?
Yeah, so in general, what we amplify is typically fundamental mode. So in terms of beam quality, it's all TM00 fundamental mode beam quality. So we offer fiber coupled as well as free space amplifier module. That depends on the seed laser concept. If that is already free space, then it's typically easier to directly take the free space one. If it is a mode-locked fiber oscillator, for example, then you can directly couple that via the fiber into our amplifier module, which is for sure the cleanest and easiest interface also.
Yeah. Mm-hmm. I see another question here in the Q&A box. What second harmonics generation efficiency did you yield from the 1030 nanometer systems?
Yeah, we typically say 50% frequency conversion to the green. This is more or less the standard which we are working with. We touched a little bit UV, but in much higher, much lower energy levels. So typically, as I said, so 50% for infrared to green.
Mm-hmm. Any other question for Mike? If not, thank you again for explaining your concept. And as I mentioned before also, feel free to contact Mike for further discussion or your interest and needs. So thank you again, Mike, for being here today.
Thank you.
And we can move now to our next speaker. So we have Gwen Pallier, Product Line Manager at Skylabs. She's going to present the fully passive beam stabilization to enable fiber launching of femtosecond lasers. So Skylabs is very well known for all these beam shaping capabilities, and Gwen is the expert in the industrial laser processing field. So Gwen, the floor is yours. Feel free to share your screen. We don't hear you now. No. You are not muted, but we don't hear you. Can you speak again, or no, I don't hear you.
Maybe go to Fabian.
Yeah, we can move. When we can move to the next speaker, and we come back to you to see if we can solve this problem with you.
Now, can you hear me?
Now we can hear you.
Okay, marvelous. I don't know what went wrong. Somehow, when you use a second screen, sometimes the computer. Never mind. Okay,
So
we're good.
Now you can share your screen.
Could say that I will try to catch up by speaking super fast, but I don't think it's advised. And I anyway.
At least not my computer. I don't know the others.
Yeah. So is it okay also for the screen sharing?
We hear like a strange gray block on the top. Now it's working.
Now it's working? Okay, perfect. So I'm here today to talk about our product Canoina USP Pure Beam, which is actually aimed to provide a pure beam, which is for us meaning that it's pure stability, and it's going to be a pure revolution for the USP world because it's a key enabler for fiber launching. So let's go through that and try to not waste time. Wasted some time already at the beginning. So I will be very short on Skylabs. Skylabs, we are a French company who is working on light manipulation for different applications. So this is our current building in Rennes. We are actually more than 170 now, if I'm not wrong. We are opening a new factory in 2027. It's going to be 10,000 more square meters, and we expect to reach something like 300 employees by then. So those are our main area of activity. So aerospace and defense is actually our main business with this optical ground station that we are selling. Our legacy product is on fiber network, but I myself, I work for now only on laser processing. And today we are here to discuss especially microprocessing. So why do we do beam stabilization? That's what I want to start my story with. So Skylabs, we do beam shaping, and we wanted to shape ultra short pulse lasers. But the thing is that they are actually monomode laser. And if you want to shape a monomode laser, it's actually a little bit challenging. And if your input is actually moving a little or changing a little, it's actually changing a lot the output, which is in then not stable. So some time ago already, like 7 years ago, we said, okay, we have to look at that because we have one main issue is that the femtosecond lasers and the setups are keen to provide beam instabilities. What does it mean? It means that typically when you change your laser power, when you change your rep rate, it will actually move typically the waist in position, in size, things like that. And in the setup, it was discussed before as well, you have thermal effect, lensing effects, which are all changing the beam and moving it. So we needed to stabilize it if we wanted to do a proper beam shaping. So that's actually what we did. And this is actually somehow the main slide, the most important result that I want to discuss today. What is the output of mode cleaner? So this is a camera. We will get back actually to all the setup later on, but this is a camera watching at the beam after a Monaco laser, 30 watt. When you don't have the mode cleaner stabilization and when you have the mode cleaner stabilization, and what you can see is that it's actually working fine. We managed to have a beam which is much, much, much more stable. And this is really a key differentiator with all the competitive technology on the market. How do we do that? Well, we actually use our core technology, which is multiplane light conversion, MPLC. MPLC is basically what you have on the right, even though currently the product don't look like that at all. This is, again, a legacy product for telecom. But the idea is that you have faceplate, one after the other, so it's implemented with two mirrors. The light is going back and forward those two mirrors. and the phase and the intensity are changed slowly so that we can control at the same time the intensity and the phase. And the key of point maybe to remember is that we only work based on modes. So it's really based on mode propagation and mode analysis. That's how we do MPLC. This system, as you can see, is actually fully passive. There is no electronic at all, and it's fully reflective, only based on mirror, which has a lot of advantages. But what is mode cleaning? So mode cleaning is using the MPLC to do the beam stabilization. So when any light is getting in the system, we make a kind of analysis of the modal content of that light. It means that we say, oh, there is that much percentage of TEM0, the Gaussian mode, there is that much percentage of other modes, and we make that analysis, and we give different roads to the different modes inside the MPLC cavity. And we make sure that only actually the main mode, the main Gaussian mode, is actually going through the system and going out, while all the other modes are actually rejected and being actually dumped. So what does it mean? That means that it's actually providing a pure stability, a pure stabilized beam. And it can manage at the same time static imperfection, meaning the beam being elliptical, astigmatic, etc., but also all the dynamic instabilities, tilt, shift, defocus, which can be due to different things based on the laser or the beam path itself. As a cost, all the energy which is actually dumped is actually decreasing the transmission of the system. So we made all the calculation, and it's very easy now to provide you with graphics. You please take note that these graphics are not going down to zero at all. So, and it's the range on which we change the parameter is actually pretty big. So it means that when we really have big shift, big tilt, or big waste change, it's actually decreasing the transmission a little, of a few percent. But we will get back to the real performance later on. So when we have done that, we have actually defined a unique feature, which is having a perfectly stable beam in any condition, whatever the input, whatever the laser is changing, whatever the setup is changing. So what do you do with that stable beam? Well, you can have a clean laser. Basically, you could just make the laser cleaner, reduce the M square, provide a very stable beam, which can be useful for some specific application where precision is required. You can have a very nice stable top hat. So that's why we did it in the first place. We wanted to do beam shaping, and the way we do beam shaping is providing extremely stable shapes thanks to mode cleaning. We can have 3D shapes. So there was some discussion about bezel beam. If you want to do very complex bezel beam, like the one which has a constant intensity over the whole propagation of the bezel beam, this is actually more complex bezel beam, and it's actually more sensitive as well to any misalignment. So to have a very stable 3D shape, you also need to have a very stable input beam. And last but not least, it's actually really useful to fiber coupling. So fiber coupling, why are we so much interested in that? Well, the thing is that we were actually talking to typically people in the semiconductor industry, and those factories are really, really huge. And having the laser, which is inside the clean room, inside for each and every station, is actually not that simple at all. Actually, it's kind of the dream that all the lasers can be fibered so that the factory is made much more simpler. If you want to fiber a femtosecond laser, you have kind of no choice but going to the hollow core fiber. So those fibers are really the best option to carry ultra-short pulses, but they can get damaged easily. So they may not be that compatible with factory environment. And when I say factory environment, I mean these thermal instabilities on the beam path or the laser parameters being changed and impacting the beam pointing. So the current solution to that problem is active stabilization. So active stabilization is basically two mirrors which are moving. There is a little bit of the light which is measured, and when the beam is depointing, it's compensating for the beam depointing. This is good, but this only can work at the speed of the sensor and at the speed of the actuator moving the mirrors. We can do beam stabilization at the speed of light, because in the end it's fully passive. The beam is in any case always stabilized. And we can compensate for any instability, as I was saying before. So what you can see now is a product demo, because I thought it's much more convincing. So I hope that the sound will work. It should work, and it's lasting 2 minutes.
Here we are in K-Labs. My name is Gwen Pallier, Product Line Manager in charge of laser processing application.
My name is Jeanne Broussou, and I'm in the technical team.
Today we want to show you how Canunda USB Pure Beam works. Let's go. So with Jan, we want to start by showing you a very simple setup. So there is a source. Then we have two injection mirrors. We extract a little bit of the light, which is going onto a first camera and to a first computer. Then actually the light is injected into our Canunda USP pure beam module, and it's going to a second camera, which is on the other computer. Let's start the demo now, please, Jan. Could you please move the source quite a lot, about a waist? And the idea is to be looking at what's happening when we are not stabilizing the beam and what's happening when we are stabilizing the beam. Okay, let's look more into details to the screens and to the numbers. Can you please tell us what are the beam dimensions?
The waist of the beam before the module is 25 microns, and the waist of the beam after the module is 35 microns.
How much the beam has moved before and after the module?
The beam has moved of 20 microns before the module and of 2 microns after the module.
Okay, excellent, only 2 microns. So it's more than 10 times less movement. We are really stabilizing the beam.
Yeah, it's really great.
So that's the real principle of Canunda USP pure beam. When the beam is moving at the input, it's not moving at the output. And it's fully passive. As you can see, there are no cables at all. Let's continue now the demo with fiber launching. After our Canunda USP pure beam, the beam is going to 2 mirrors and then injected into the Photonic Tools module. This module injects into that hollow core fiber, which is going to that laser head and to that camera, and we are looking at the camera onto that computer. Hollow core fibers are really beautiful, but they are very sensitive. If the beam is not injected perfectly into the core, when you have high power, you are actually damaging the fiber. Can you show us now what's happening when the beam moves without stabilization?
When we are moving the mirrors, we can see the light goes into the higher modes, which would damage the fiber.
Can you show us now what's happening when the beam moves and there is stabilization?
We can see that only the transmission is decreasing.
With Canunda USP pure beam, no light in the higher modes.
And your fiber is safe.
Okay. So that was a product demo. I think it's quite convincing. Let me go to full screen, next screen. And the idea is really that you enable to, in any case, not have any light in the higher modes. And in any case, you cannot damage the fiber. So at worst, you can decrease the transmission, but you cannot damage the fiber. So that's really changing the game for fibering. Okay. So I will be quick on the impact. Yeah. Running out of time.
We hear you with some interference for 30 seconds, but now it's working again.
Okay. Yeah, well, let's hope that my main message can be at least read on the slides. So why it's a game changer? Well, first, it enables to have smarter factory. Typically, you can reduce the number of laser per station, because whenever you have a problem in the laser, you don't have to switch to the second laser. You could just unplug and replug. You don't have to realign everything. So it's really, really impactful for the big factories. It can also simplify the optical path inside a machine. So instead of having all these mirrors and all these optics that the machine builders have to align, well, you just have the fiber going directly from the laser to the scanner. And it also enables large-scale processing. So at last now you can put the laser onto a robot arm, which is not possible with free space laser. So all this is really game changer. I have a lot of technical results, but I will be lacking time for that. I will be very quick. So I just want to say that we have actually demonstrated that the transmission is not changing over time when we are in real industrial condition. So it is stable over time, whatever the transmission is. Once it has compensated for the beam quality, it's actually really not changing. So it's important for process stability. We also demonstrated that typically with a Monaco laser, when you are changing the power from 0 to 100%, it's also not changing the transmission, which is very stable. Again, it's quite important for process stability. And we did demonstrate that we could divide, in that case, the pointing by more than 6 with such specific setup. So that's it for today. I hope I convinced you that by providing pure stability, we can actually make much more practical fiber injection, especially at high power. And this is it for me for today. I'm open for question if there is time.
Thank you very much, Gwen. So we have time for questions. I have a question regarding the power level of the lasers that your solution is working for. And as I made to Mike, perhaps the requirements of the laser when connecting to a source, if you have any previous requirement, any optical component that you need before your system.
Yeah, it's an excellent question. It's not just power in the end, it's also about energy, and it's also about peak power. So right now, we have two systems, one which is more optimized for lower power, up to 30 watt in the IR, and one which is optimized for higher power. So it means that there is more thermal management that we have actually specified at 150 watt in IR again. And now when it comes to energy, so we have specific designs which can go up to the millijoule, but the off-the-shelf version is 500 microjoule at 300 femtosecond. But then if you have actually longer pulse, we can take more energy. It's more about the peak power, the peak energy, than about the energy itself. And the other question for the beam adaptation, well, the thing that we made at last, I think I was waiting for that for some time, but we made at last the move to have standardized input which are larger. So the beam adaptation is actually simpler now. So still you need to inject. So like any module that you want to inject, you need two mirrors to adjust the injection angle and position. And then depending on the laser, you may even not have to adapt the beam size. But of course, one standard module cannot work with all the lasers in the world because they have very different beam diameters.
Yeah, understood. Any other question or comment for Wen? So I don't see anybody here, so please feel free to reach her for further discussion as well. So thank you very much, Wen, for being here this afternoon.
Thank you very much. Bye-bye.
And we will finish today with the final presentation by Fabian Sorensen, Senior Product Line Manager at the company Coherent, a worldwide known company, and he's going to present the next generation components for large-scale deep UV ultra-short pulse applications. So Fabian, thank you for being here. The floor is yours.
Thank you very much. Thank you for the opportunity to speak. Let me share my screen. I hope you can see the screen now. Okay. Yeah, so today I'm going to speak a little bit on behalf of my colleague Alice Zhang. So as you mentioned in the beginning, Coherent is a very large company, worldwide operating company, potentially right now the largest photonics company in the world. Just for anybody who is not aware of the background, so we are a company originally founded in 1971, basically with the merger with 26, formerly known company 26, 2 years ago. We are now at 26,000 employees worldwide and roughly a $6 billion company. The merger originally brought two areas together that kind of make sense. So the laser world that I'm coming from, so I'm located in Kaiserslautern, Germany, where we develop our ultra-short pulse lasers. I'm responsible for the development and the product lines in our ultra-short pulse portfolio. But it also brought in to the same company, a company that is formerly known as Photop, so a materials company producing optics, optical components, mirrors, and complex optical systems. And I'm presenting part of my presentation today on behalf of Alice Zhang, the product line manager from our advanced optics group, on next generation deep UV components. And I wanted to start with the question on, does wavelength matter? Why are we talking about deep UV ultra-short pulse lasers in the first place? And I wanted to highlight two main applications that are currently driving this development and why we are pushing for this topic so much before going into some of the key components for this. One of the driving applications is the display manufacturing, OLED display manufacturing world, where there is a strong push for bezel-free displays. So really the push for better and better cutting qualities, but also the push for minimized delamination caused by using UV lasers. So the positive record is using pico and femtosecond lasers and 355 or 345 nanometer wavelengths. But they actually have an impact on UV hardened glues and adhesives. So going for shorter wavelengths has the advantage that these adhesives are not pre-hardened like they are being when using 355 nanometer. And this combined with the benefits of better ablation of the 266 nanometer wavelength actually pushes forward really the quality that can be achieved when talking about a complex stacked material like OLED layers. And there's a full study on this where we compared picosecond UV, femtosecond UV, and picosecond deep UV lasers for this particular application. Then we presented earlier this year at Photonics West, and the paper is available for download. The conclusion of this, I just wanted to show you here to basically bring my point down. We make direct comparisons of the process of records using picosecond lasers and femtosecond lasers and what would be theoretically possible in terms of the best operating conditions. And what you can see is that pico and femtosecond lasers have very similar cutting efficiencies for 355 or 345 nanometers at the optimum. The process of record shows that femtosecond are more efficient. That is mainly due to the much wider process window. So it's much easier to find the optimum for a femtosecond laser, usually giving you a better and more stable process. But when we then compare this to deep UV really unlocks an unseen cutting efficiency for this multi-layer material with complex absorption coefficients. For every layer, it's very different. So you want to, so it's complicated to find the right process. But DPV has shown to be better in quality and is the much more efficient process. So in theory, you could go much faster as well when you have the same power and energy available. So that was one important step to show this. But there's a big challenge here, which is making the right power available to actually compete with the 50-watt UV standard that is currently for femtosecond, picosecond. We needed a laser that has sufficient power in DPV, and I'm going to get to that in a minute. The second application I wanted to highlight as a driver for why going for DPV is semiconductor processing. In this particular case, we've shown in a study the comparison of UV and deep UV ablation for planarization of silicon carbide wafers. And what you can see on the left is ultimately just the result, but what you see here is comparisons of the two different wavelengths at different energy levels, effectively going above the normalized, or going above the fluence threshold, so effectively the energy deposited in the area. And there is a threshold fluence to actually achieve ablation, right? So you need to increase, you need to be above that threshold to actually ablate the material. And when you basically normalize the energy by using the fluence you use divided by the threshold fluence, you get kind of a good factor of comparison between two different processes using two different lasers. And what you can see is that when you increase and go significantly above the fluence threshold, you still have a very good result and very good process with 266 nanometers, while with 355, you get waves in the surface, and actually at higher energies, when you go further beyond the threshold, you get melting effects. And these melting effects did not show up when using DPV. So here's a huge potential to use DPV in planarization, but in generally using it for all sorts of ablation-based processes for silicon carbide, certainly, and we see similar results and similar effects for silicon-based wafers as well. So if this technology brings so much benefits, what do we need, right? What are the components that are required? And in my responsibility is the laser. And we released already years ago a DPV picosecond laser with 10 watts that is now in mass production and has been adopted and is a proper industrial tool. But we recognize that to achieve the throughput that is required for these type of applications, we actually need much more power. So the next thing that we are doing now is doing a 20-watt DPV system. We already have that in our laboratory. So the first prototypes have been built and we have live tests running. So this data shows it's over 22 watts at over 8,000 hours. Actually, I don't have the graph in this presentation, but we just stopped the live test after 11,000 hours and will now make changes to some of the design and then finalize the product. So this will be launched very soon. We've proven that this can be done at very good results. The main aspect here is not only the lifetime of the crystal, not only the lifetime of the harmonic generation module overall, but mainly it is that the laser is stable under all operating conditions and that it's freely modulated, or that you can freely modulate the laser output just like you would with any UV or IR or green laser. So you can gate the signal without having power ramp ups once you open the gate. So it's really very, very stable, and you can use it for industrial grade micromachining applications. So fantastic. So now we have a 20-watt laser, but how do we actually get it to the material? And so here comes Alice in, and I want to highlight at this point, I've been called within the company, I've been called the DPV evangelist. So I've been telling everybody who wants to hear it that DPV is kind of the future of ultra-short-pulse processing. And we've been working with multiple companies. There are many companies that we've been happy to collaborate on providing components like I'm showing you. Overall, we want to push forward this field. So we're not exclusively showing technology that only we can offer, and there are many companies that I encourage you to engage. Celoptics is on the call, so they have fantastic components for this as well. I just wanted to highlight this because from my perspective, this is a collaborative effort to push forward DPV for industrial processes. But I wanted to show you components that will be required if you actually want to go for large-scale processing of DPV. For example, for the display cutting business, we will need f-theta lenses, telecentric f-theta lenses at significantly larger scale that are ready for DPV. So what you see here is a DPV f-theta lens that is with a scan field of 200 by 200 millimeters. So this is a very huge piece of optic, and is really critical to identify what material to use if you actually want to use it at a high energy, high average power deep UV ultra-short-pulse lasers. So we're talking about very, very high intensities that usually standard fused silica will not survive. So standard fused silica optics will degrade in these kind of laser setups or beam delivery setups. So you need not only a f-theta lens of that size, but you also need an f-theta lens that is made out of a material that can last and can withstand the laser light. That's very aggressive and very, most of the materials is absorbing this light very strongly. So the team that, so I'm presenting here for Alice and her team have developed material combinations because the obvious choice would be go for calcium fluoride. And calcium fluoride is very expensive and very heavy. And when we talk about an f-theta lens of this size, anybody who has any background in this will know if you try to make an f-theta lens of 30 kilogram calcium fluoride, we might not ever see this in mass production simply because of the cost of that material today. And we need a technology that is not making this solution prohibitive in mass production. So development of material combinations of fused silica and calcium fluoride with the right coatings have come to success here. And I will share a few data points in a second, but I wanted to point out another key component that is needed here, because if you want to work safely with an f-theta lens, and if you don't want to use calcium fluoride, you need to use larger beams, right? So you want to go for entrance beams of 40 millimeters. You really want to use 40 millimeters. If you go at smaller beams, the chance of you damaging the optic is really high. So we encourage everybody to use beam expanders. And the beam expander is critical because it's very unlikely that out of the laser, we will make a laser design that has a 10 millimeter or 50 millimeter beam output, because that's not really ideal for the conversion efficiency. So we could include the beam expander already within the laser to give you whatever laser output you would require. But not only does that leave you with less flexibility on your process, but it also turns out that the beam expander is a really, really critical component because at this point you are prone to having beam sizes smaller than your originally input aperture, which increases the risk of damaging the optics even further. So in our experience, it has been key to have beam expanders that are using high quality materials, high quality designs to either have a fixed beam size or a variable expansion factor for your processes. And having this designed with calcium fluoride optics to ensure that you don't have degradation and only have to align this once and not every couple of 100 hours once the optic degrades was really important. So these are the two key developments that we wanted to do on our side, just as some other suppliers in the world have been delivering solutions for this. But we felt it was important that we can provide customers components of all three critical aspects. We don't have scanners. Right, so that will be the fourth critical aspect here, but having the f-theta lens, having the beam expander, and having the laser is really accounting for some of the key components when you want to design a DPV system. And I want to leave you with two more informations. One is we did a design based on these f-theta lenses. If you work with this kind of size, this scan field size, right, 200 by 200 millimeters, you have to look into your spectral bandwidth of your laser. And we've done simulations with different materials that we've been using, different f-theta lens setups, and we've tried to see where is really the limit. And what you can see here is that already with a spectral bandwidth delta of 20 picometers, you see a deformation in the beam profile through the f-theta lens. That tells you, and this is kind of the extreme here, right? But this is a 200 picometer spectral bandwidth variation. So that basically means a 0.5, 0.4 nanometer laser spectral bandwidth laser will basically get you terrible beam quality out of the f-theta lens. And this jumps back to the beginning, why we analyze picosecond, femtosecond against each other in these applications. Because when you work with a femtosecond laser, you will be struggling at these sizes of f-theta lenses. So there are some advantages on the lasers themselves when using picosecond for conversion efficiency, but when using the f-theta lenses, clearly the much shorter spectral bandwidth of a picosecond laser, which is currently at around 20 picometers, gives you big advantages when working with really these large size f-theta lenses. So that's why we focus on the combination of a picosecond DPV laser, the beam expander, and this f-theta lens. And last but not least, I know I'm running a bit out of time. Just to leave you here, we've done this with multiple coating. We do our coating ourselves in our facility in China. We do the entire development of the optic components, the sourcing of the material, and the coatings. So we have solutions for that and can provide specific solutions for your applications, not just for 266. We can go to shorter wavelengths. but we can also go to longer wavelengths, obviously, and we have the standard optics available. And this is something that the team in China has been doing for many years and has designed specific optical components up to complex optical systems. And that's what I wanted to leave you with. Thank you.
Thank you very much, Fabian. So we have time for questions for Fabian. I will perhaps have a question because you mentioned that this kind of implementation is a collaborative effort. So going back to the EPIC question is how other companies can support Coherent in this process. Do you have in mind any potential collaborations, interest of Coherent in collaborating with other companies?
Yes, so I mentioned at the beginning that some of the companies that are on the call today, we've been working on for this. And I think that from my perspective, collaboration is key here in finding a solution that is workable. So on every aspect of the beam delivery of DPV, be it the optical components, the mirrors, the coatings, but also we're talking about the beam path needs to be completely purged. So we need clean, dry air supplies. We need really solutions that deliver the 266 light to the table efficiently. And at every aspect of this, customers that try to implement this today run into roadblocks of technologies that are not available yet or simply not withstanding the intensities of ultra-short pulse DPV light. So we're looking for anybody who's interested in collaborating on developing parts of the solution here. And there are optical companies that we've been working with together for some of the optical components, which we really appreciate, and we want to continue to do so. And if there are other companies who have good solutions for how to make the solution more stable and longer lasting in the field and bring down cost ultimately, this would make this more usable, because I think there's no question in my mind that it actually brings a benefit to almost all the applications that we see. So right now it's more about getting the cost down and getting it into a state where mass production is feasible for a lot of companies.
Okay, thank you very much for the answer. I don't know if there is any other final question for Fabian. If not, thank you. Thank you again for putting also this topic on the table. And thank you, everybody, for being with us today, this afternoon. I hope you enjoy all the presentations as much as I did. And here you will see the poll that we always do in our online meetings. So please take the time to answer, and it will help us to improve our future events. And from my side, just to wish you great Christmas, a great end of the year, a great final days also, because I know that in the business December is also a crazy month. So good luck with the end of the year, and I hope to see most of you next year. Some of you probably in Photonics West, but also in other events. And just to remind that we will have our event in Amplitude next year. Again, I can share my screen. So remember that 4th and 5th November, we will be in France, talking about micro-cutting, micro-dealing, all the ultra-fast laser processes that are interesting for different industries. So I invite you again to join us, and also the rest of the online meetings. So again, thank you very much for being here today, and I wish you great Christmas, great start of the year 2026. Goodbye, everybody.
Thank you.
Thanks, Antonio. Bye-bye.
Bye-bye.
Bye. Thank